Hi everybody, it's Dr. Chabot, and I made a thing to try to help us with that problem we're working on related to the physical pendulum. So this is the physical pendulum. It's a series of 3 rings, and here's the pivot at the top. So it oscillates like this, as we see in the diagram. So that's what it's showing. And a lot of times when we look at the pivot, imagine that there's a long rod. That's the axis of rotation. So if I kind of show you what the axis of rotation would look like for this, we can see there that the object oscillates as if it's rotating around that axis. And that's important because with the parallel axis theorem, you need to have that first term be the ICM, the moment of inertia through the center of mass if it was a parallel axis. So we need to figure out which term to use for each ring. So again, our axis of rotation kind of points into the pivot, and that's our visual there. So I'm going to go ahead and share screen for a second. Okay, so as you can see from what I've drawn here, when we use the parallel axis theorem, this first term, ICM, comes from our tables of moment of inertia, and we need to use the object and the moment of inertia for our object that has an axis parallel to ours. So for example, in this ring, it's tricky because on the table, there are 2 moment of inertias for the hollow ring. One is 1/2 mr squared, and that would be for an axis that points along the plane of the ring so that it rotates as I'm indicating here. And I'll do that on the larger video as well. But that's the rotation for 1/2 mr squared. On the other hand, we also have mr squared, the full mr squared, and that would be the typical pivot through the center, and the ring is rotating around that center point. So when we are analyzing our object, which again is going to, oops, my pivot fell out, which is going to rotate like this, we need to look at each ring individually, and we need to decide which axis through the center of mass is parallel to our axis. So let's go ahead and just do this one by one. Again, here I'm actually indicating not just the pivot, but the axis. So we can visualize our axis, and then we can see which one is going to be parallel to it. So I'm actually going to start with this outer ring that I'm touching right now. So this one right here, that's going to be our outer ring that we're actually seeing face on. And if we look at this oscillating, we can see, and if I isolate it, I can just use this one here, it's doing this. So that's going to be what it's doing. It's rotating around that rod. The pivot is in, like, away from me, and it's rotating like this. We can see that that is indeed parallel to the one that goes straight through its center. So for that ring, we need to use the mr squared term. Okay, you might want to write that down. Let's talk about the other rings now. So that took care of this ring that we can see right here. And so now let's talk about the ring that we're seeing edge on. So this ring that we're seeing edge on, let's isolate it and see what it's doing. So we're seeing it edge on. Our axis is actually parallel to it, and it's basically doing this, right? Okay, so if it's doing this, then we're going to move our axis down. We can see that it's actually parallel to the one that rotates as shown. All right, so that is different than the other ring. Very good. So now the last ring, if we look at this again, our last ring isn't even attached to the pivot. That's okay. It's still oscillating relative to this pivot and to this axis, and it's oscillating, around this axis. So again, let's isolate it. So this is now this horizontal ring, right? So let's see what it's doing. So it's down here, my axis is up here, and it's oscillating basically as I'm shown here. Let me try to do this. It's kind of going like that, right? So it's oscillating around this pivot here, and I want to lower it down, and I see that it is actually parallel to that axis here. So this axis that crosses it like that is what it is parallel to. Okay, so that takes care of what you would use for the first term in each of these. As for the second term, don't forget about the second term of our parallel axis theorem, where we want to make sure to take into account how far our axis has shifted. That part of this problem is a little bit easier, so I'll let you just look at the diagram and reason through that yourself. Okay, I hope that this 3D visual helped clarify what's happening with each of the rings. You can find the moment of inertia through the parallel axis theorem for each ring individually. So we have that one, we have that one, and then we have this one. Find those 3 moment of inertias, add them all up. That's the total moment of inertia of your system. And that M that's there, that's the mass of a single ring. The total mass is 3m. So keep that in mind when you're doing your calculation as well. All right. Good job, everybody.